Next unit, unit 3, concept of stability and Raoult-Hurwitz criteria. That is unit 3, concept of stability and RH criteria. Now, first we will concentrate on concept of stability. Yes. Now, if you take any system, there are various ways we can explain the stability of the system. That means the response of the system. Suppose we have a bounded input and bound output. That system is called bounded BABO stable system. That means if the input is bounded and output also bounded, then you can say it's a BABO stable system. Then one more type is called asymptotically stable system. Then absolutely stable system, then marginally stable system, unstable system. Different types of systems are there. First we will see what is meant by BABO stability. BABO stability means if a system produces bounded output for the given bounded input signal, then the system is called BABO stable system. I'll write here, if a system produces bounded output for the given bounded input signal, then the system is called as BABO stable system. Yes. In continuation, the stability refers to the stable working condition of the control system. That means the output or response of the stable system is predictable for a given bound input signal. So that's called stability, right? So the stability refers to the stable working condition of the control system. That means the output or response of the stable system is predictable for a given bound input signal. For a given bounded input signal. Yes. Next category is asymptotically stable. What is an asymptotically stable system? That means if a system output tends to 0 in the absence of input signal, irrespective of the initial conditions, the system is asymptotically stable system. You know, if a system output tends to 0 in the absence of input signal, irrespective of the initial conditions, then the system is asymptotically stable. Then the system is asymptotically stable. The next category, absolute stable system. Absolute stable system means if the output system output is bounded or stable for all the variations of its input parameters, then the system is known as absolute stable system. Right? If the system output is bounded or stable for all the variations of its parameters, then the system is known as absolute stable system. Absolute stable system, yes. And the next category is unstable system. The next system is unstable system. That means if the system produces infinity output signal, if the system produces infinity output signal or the oscillatory output for bounded input signal, then the system is called unstable system. Then the system is called unstable system. The next category is marginally stable. Marginally stable or conditional stable system. Marginally stable or conditionally stable system. The system, that means if the system produces constant amplitude, if the system produces constant amplitude oscillations for bounded input signal, then the system may be stable or unstable. Depending upon some constraints, this type of system is called marginally stable system. Marginally stable system. The next category is limitedly stable system. A limitedly stable system means there should be some range. Within that range only will be stable. The remaining will be unstable. That means if the system output remains bounded or stable for a limited range of variations of parameters, then the system is called limitedly stable system. That means if the system output remains bounded or stable for a limited range of variation, or limited range of variation of parameters, the system is called as a limitedly stable system. Then the system is called as a limitedly stable system. Next, location of roots versus stability. The next concept is location of roots versus stability. Right. That means for a stable system, all the roots of the characteristic equation should lie on the left half of the S-plane. Then only system is stable, otherwise unstable. Suppose if I take a plane, the S-plane, this is j omega, this is real axis sigma, okay, S equal to sigma plus j omega. Yes. So for a stable system, all the roots lies in the right half of the S-plane, RHS. Then system is unstable if the roots are lying in the left half of the S-plane, LHS. The system is stable system. If the roots are lying in the imaginary axis, then the system is oscillatory. Okay, that means for a stable system, all the roots of the characteristic equation should lies on the left half of S-plane. Now we'll continue depending on the roots of the characteristic equation location in the S-plane. We will see diagrammatically how the system respond. Yes. First category, transfer function and location of roots. Location of roots. Here is impulse response. Impulse response. Impulse of first category. Just you take the roots. This is real axis, imaginary axis. A is minus A. So the transfer M of S equal to A by S plus A. Now its response, impulse response will be like this. impulse response m of t. So c of t equal to a into e power minus at 0. Okay. Let us continue the allocation of roots versus stability concept. First, we'll see the transfer function and its location of roots and corresponding impulse response, how it is moving. First, the transfer function. And its location of roots, then impulse response. Impulse response. First one, ms equal to a by s plus a. If you see, locating the s plane, this is the real axis, imaginary axis. This is minus a, s equal to its impulse response. M of t, that is m of t equal to a into e power minus at. This is time. Next function, suppose if I take ms equal to a by some s plus a and s plus b. Again, this is minus a minus b, real axis, imaginary axis. So m of t response a1 e power minus at plus a2 e power minus bt. Okay. Next, that transfer function, suppose complex roots are there. a by s plus a plus jb into s plus a minus jb. These are the complex roots, plus jb minus jb. Its corresponding impulse response is so m of t equal to a e power minus at sine omega t. Next, a type, the transfer function a by s square plus b square. You will get simple imaginary roots, plus jb minus jb. So here s square plus b square means s square equal to minus b square and s equal to plus or minus jb. Yes. So you get a plus jb and minus jb. That response is this is m of t equal to a1 sine omega t. So if you get imaginary roots is oscillatory, so the response is a sinusoidal response. Then next type is a by s minus a. That means roots are in the RHS, imaginary axis, real axis. So its response is exponentially increasing function. It's a. So m of t equal to a into e power at. Yes. Okay. The next transformation type, ms equal to a by s. Suppose a root at the origin, simple pole, that is the imaginary axis, real axis, a pole at the origin or a root at the origin, you will get the response as step response. Step response. So m of t equal to a into u of t. Yes. The another type is transformation a by s square. Suppose we have multiple roots at the origin, like a double pole at the origin, then the response will be like a ramp. This is imaginary, real. Okay. So m of t equal to a into t. It's a ramp signal. Suppose we have m of s equal to a type of transformation s minus a minus jb and s minus a plus jb. That means roots, complex roots which are lying in the right half of this plane. This is a plus jb minus jb. So its response is exponentially increasing function. It's oscillatory but exponentially increasing. So you write the transformation response a e power at sin omega t. The next type of transformation is, suppose we have the roots on the double roots on the imaginary axis. For example, a square plus b square whole square, then you will get double roots on the imaginary axis. Real and imaginary. Then the response will be like this. So this is the concept of stability. So depending on the location of roots, how the system response will change. It's oscillatory or unstable system or stable system. So depending on the location of roots we have explained now. The next concept is Routh-Hurwitz criteria that I will see now. The next topic is RH criteria, means Routh-Hurwitz criteria. Routh-Hurwitz criteria. So what is meant by what is Routh-Hurwitz criteria? How it will be useful? Actually, you have if you have any polynomial equation like characteristic equation, higher order equation, then to find out the system stability, we can use this RH criteria technique. Suppose if the roots of that polynomial equation factorize, if it is lies on the LHS of this plane, then it is a system stable. If it is lies in the RHS, the system is unstable. So with this criteria, RH criteria, Routh-Hurwitz criteria, we came to know that the system is stable or unstable, and if it is unstable, that means there is roots in the RHS. So we came to know the number of roots lying in the right half of the S-plane also. That is a best useful a technique to find out the number of roots which are lying in the RHS. Suppose so there is one criteria like Routh array. So in that we will see the number of sign changes in the first means elements of the first column of Routh table. That will gives the number of roots in the RHS. So that we will see in detail now. First, in RH criteria, the location of roots of the location of roots of characteristic equation is examined by using Routh array. First point. The next point, the number of sign changes, the number of sign changes of the elements of first column elements of the first column of RH table or RH means Routh array, first column of Routh array gives the number of roots which are located on the RHS of S plane. S plane. So in this, there are different cases are there. Case 1, if there is no sign changes in the first column elements of the first column elements, then the system is stable. That means all the roots of the system are lying in the left half of the S plane. First we'll do the figure case 1. If there is no sign changes in the first column elements, then the system is stable. Then the system is stable. That means that is all the roots are lying on the left half of S plane. Left half of S plane. Next case 2. Case 2. If there is a sign change in the first column of first column elements of route array, the system is unstable. If there is a sign change in first column elements, of route array, then the system is unstable. Then the system is unstable. Then the number of sign changes gives the number of roots located in the RHS of S plane. The number of sign changes gives a number of roots located on RHS of S plane. This is another case. Okay. Then what is the necessary condition for stability? The necessary condition for stability. First condition, all the coefficients of characteristic polynomial should be positive. First we'll see what is the polynomial equation of characteristic equation. Characteristic polynomial equation. Characteristic polynomial equation, that is Q of S. So Q of S equal to A naught S to the power of n plus A1 S to the power of n minus 1 plus A2 S to the power of n minus 2 and so on plus an minus 1 into s plus an equal to 0. So in this equation, the first condition is all the coefficients of qs should be positive. Next condition, there should be no missing terms in the polynomial. There should be no missing terms in the polynomial. This is the a necessary condition for stability. The next, what is the sufficient condition for stability? Sufficient condition for stability of the system that is, all the roots of characteristic equation must lie on the left half of S plane. However, one root is allowed at the origin. That is the sufficient condition. All the roots of characteristic equation must lie on the left half of S plane. However, one root is allowed. However, one root is allowed at the origin so this is a sufficient condition for the stability of the system. Okay.